Hello YouTubers! In this video I will present a new method how correctly calculating aeroplane wing length force works, and the same mathematical model will be applied to maximum turbine windmill blade torque/moment numerical calculation. The video will be long with numerical values examples, but beneficial because it will show many misconceptions that exist in designing optimal wing or windmill turbine blade shapes. Here from the scientific paper. All reference and links cited here are in the description below. Criticism of Kuta-Zhukovsky-Prandtl. In the picture, lift by circulation according to Kuta-Zhukovsky. Potential flow with zero lift drag resulting from high pressure at flow separation on the upper wing surface before the trailing edge of the wing. Being modified by large-scale circulation into a Kuta-Zhukovsky solution with the high pressure shifted to the trailing edge, thus changing the direction of the flow downwards after separation downward, and thereby creating lift by Newton's third law. High and low surface pressures are indicated in the picture. First criticism: lift by circulation might be true, but it has no experimental or mathematical model to back up this theory. Secondary citation. Experimental evidence shows that the classical explanation of lift from circulation by Kuta-Zhukovsky is incorrect, since there is no high pressure buildup at separation, and the classical explanation of drag from viscosity effect by Prandtl is also incorrect, since the lack of high pressure at separation gives a significant contribution to the total drag. But the classical theory is deeply rooted as expressed in example. The origin of lifts. Without viscosity there would be no lift, birds and aircraft would not fly, and sailboats would not sail. No viscosity, dynamic or kinematic, only steady air density at subsonic speeds. Viscosity introduction into wing or turbine blade lift theory made theory incompatible with reality. It has notations subscript infinity, velocity and density. Our fluid density and the fluid velocity far upstream of the airfoil. It will be our task to reverse engineer from maximum velocity density at subsonic speed is constant before contact with the airfoil, which is a scientific term for wing, and afterwards. The biggest blunder of fluid mechanics is viscosity, a non-dimensional Reynolds number. Computer science, yes, is useful to simulate realistic flow and visualize turbulence of fluid where energy conservation conditions are not important. But for physics later adapted to engineer its biggest mistake. Solution of simple shape fluid flow in pipes, channels and wings in which an airfoil is a rectangular plate or plank. Longer path, equal time transit theory based on Bernoulli hydrodynamics equation. The top of an airfoil is shaped to provide a longer path than on the bottom, thus velocity of the bottom streamline is bigger than the less curved bottom of the airfoil. Thus from Bernoulli hydrodynamics equality we got that pressure must be higher at the bottom of the airfoil wing, thus lift is produced, delta P. I have only ever encountered with equal transit time theory when it is being debunked, so it seems like it's more common to see it pointed out as wrong rather than alleged to be true. It gives no explanation why air molecules must meet at the same time on the end of the airflow edge. Hypotheses or assumptions streamlines of upper and bottom air molecules moving with different speeds must meet at the same time. No scientific evidence exists which confirms such claim. We can eliminate this theory based on a lack of evidence. Praises goes to the YouTube channel Fly with Magnar, who was or maybe is a pilot, and Professor Holger Babinsky, University of Cambridge, Department of Energy, Fluids and Turbo Machinery, also made a YouTube video essay debunking some misconception about wing lift, including the infamous equal transit time theory. Even though we give detailed explanation about flaws in existing theories, I disagree with Fly with Magnar on theory lift theory. For example, here lift is a drag non-dimensional coefficient relating to airplane velocity, and that it is mean thrust. In my method, the only form which is wing angle of attack is matter for lift force. Later we will see that any kind of drag is a negative factor. With Holger Babinsky and Magnar, I disagree on one crucial: the wing, which is airfoil, can be flat plate. Yeah, only the angle of attack theta gives lift with wind velocity for stationary turbine blades or wing. Credit needs to give to Holger Babinsky. In his paper, he derived the Bernoulli hydrodynamics equation from second Newton law of motion. Holger Babinsky, How Do Wings Works? You can find PDF file online for free and see that. I disagree that airfoil need curvature, and airflow over curvature creates centrifugal force that produces lift. It is not needed. Our example will be a wing flat plate or plank. The joke on me is that I belong to flat wing or flat blade society. No lift drag equation is required. We have maximum CD0 equal unit 1, which is a plate perpendicular to the wind flow with velocity W0. Later, the same cross-section area plate has a cone shape with wind velocity W0. Thus, drag coefficient is equal to. That is very important moment. The values that are bigger than 1 are incorrect based on energy conservation condition. All our values can be debatable, but any value that is bigger than unit 1 implies you can create a sail that on some shape and harness wind velocity less than the maximum value W0. We can make the thought experiment where a massless particle blown by the wind with velocity W0 less than wind velocity. That is wrong. That is violation of energy conservation condition. In a chapter titled Numerical Solution of Airplane Wing Attack Angle Theta in Straight and Level Flight Position, we will show how we can calculate pressure losses and velocity losses by applying the reverse engineering method to physics problems for airplanes where engine thrust is well-known value. We will see that airplane flight velocity is always less than the maximum thrust velocity produced by propellers. Airplane or rocket thrust produce much higher thrust and velocity than the actual velocity of an airplane or rocket in flight. Propeller thrust must compensate for induced drag forces. The misconception in the present theory is that airplane velocity is also related to drag coefficient. That is the same claim that also untrue that for a mass of an object in second Newton law of motion where a force divided by acceleration is equal to the object mass. The basis of a new theory, drag force, is a negative factor that required for lift and are independent of wind velocity or airplane produced maximum thrust force. The second test is maximum drag is between 0 and unit value. Maximum gain force is equal to maximum wind velocity W0. Velocity can be a relative measurement unit. For example, wind velocity in a wind tunnel experiment where the aerodynamic object is stationary and artificial wind is created by powerful draft fans. First, we start with turbine plates are two very thin plates or planks. Blades are not just thin but also very rigid, which means no Hooke's law is required to estimate blades bending or twisting due to elastic deformation. Theory and existing terms in condition that single blade is parallel to wind velocity W. In the picture, wind velocity W hits the blade under the angle less than 90 degrees, which means some of the velocity slips over the turbine blade with velocity we shown here. Here no shear friction happens, only drag force involved. The drag force shown here is noted as Fd0, solved according to this equation. Here N is nominal force, always perpendicular to the blade surface area, and in the end lift force Fl is equal to. Lift force is a product of two terms. At the same time we have drag force in x-axis direction shown here, and lifting term in the y-axis direction here. The product of both drag force in the x-axis direction and y-axis direction under the angle theta produces lift in the y-axis direction Fl. Blade element moment theory developed before Brouwer's flight is a highly simplified but useful approximation in the Rankine-Freud momentum or actuator disk model. Wikipedia source has such force equation. F theta is the force that is responsible for the rotation of rotor blades. F zeta in our case in the x-axis is the force that is responsible for bending of the blades. I agree with equation on the one crucial fact. In our case, in the x-axis direction is bending force, which is a negative factor that wants to break the turbine blade off, and in the y-axis direction we have positive force term of rotation / bending or moment / torque. That is a crucial difference between Rankine, Freud and the math model presented here. Blade element moment theory is that they add and subtract term lift and drag shown here. In my case, junction and is a logical operation of multiplication. Lift and bending are simultaneous actions Thus, in the formula we have product mass operation of both terms. The last unknown term is maximum blade surface area is equal to. The next step is to calculate the maximum velocity U max and maximum torque moment M of the turbine blade in a context where a turbine blade asymmetrically angled operates as lifting wings. One method is algebraic to calculate the maximum angle at which lifting force is maximum by applying the Fermat principle to the least action from an angle variable. Another method is to solve is by plotting a graph from the angle variable. We apply the Fermat least action principle, finding the derivative of a lifting force function and later equating the equation to zero. In front of the function, we have a constant force term, independent of the angle variable. That is not full derivation because at a 90-degree angle we induce drag force in the y-axis direction. To solve the drag iron resistance of the rotating plate, we multiply the equation above by sinus theta and cosine theta product and again apply the Fermat principle of least action. The last equation shows an ideal condition and fundamental law of physics for a plane turbine blade maximum angle to harness maximum wind velocity energy is equal to 45 degrees. For any number k bigger than and equal to of blades, and if a shaft of blade is not connected to torque required device, for example electric generator, bearings are frictionless, blades are made from ideal rigid material, no twisting and bending of blades according to Hooke's law for elastic materials. Thus, maximum blade rotation linear velocity is. This maximum linear velocity is the fundamental law. It means you cannot design better blades that harness more than half wind velocity. In closed design, for example, superheated steam turbines or hydro dams, electric generating power plants, laws and maximum values are 100% different and can be independent of turbine blade curvature or angle of attack values. According to Bette's law, no wind turbine of any mechanism can capture more than 16 divided by 26 or approximately 16% of kinetic energy of the wind. In my theory, 25% of the kinetic energy of the wind or 50% of wind velocity can be converted into useful rotation velocity U max. The difference between Bette's and my theory is that the Bette's limit is based on open disk actuator. It means a hypothetical turbine without any geometry description, curvature, maximum blade number, angle of attack value, or info on the surface area of a blade. Weber isobars show that in the location of a stationary turbine tower before and after wind velocity stays steady. We care only about the wind velocity part, which can be converted into useful torque. For closed turbines inside the chamber, for example steam compressed air, hydro pumps and ventilators, geometry can be ignored. The maximum pump flow rate is known in pump specification by the pump manufacturer, and design pipeline we calculate total loss of pressure / flow rate. In this instant, pump impeller geometry is not important. However, for open windmills or aeroplanes, geometry and surface area of the wing or blade are essential parameters. In case mechanics, concentrated load is calculated according to this equation shown in picture. In our case, with velocity, we have uniformly distributed the lifting force of wind over the entire blade length, capital letter L, shown in the picture here. Torque force is uniformly distributed according to parabola equation, and the total turbine torque force for a blade turbine is equal. The 45-degree angle of a turbine is most optimal under a low velocity wind. If we have a hurricane type situation, wind velocity angle of attack can be minimized near zero with angle pitch mechanism. Later we will see how an airplane wing angle of attack changes its lift performance from angle of attack change. Torque is a most important term. It shows maximum capability to rotate an electric generator and convert mechanical torque into electric energy. Here we investigate an aircraft small-scale model in a wind tunnel with maximum velocity W0 equals 45 meters per second velocity. The choice to make a model and a windmill turbine is a reason that they operate on the same principle as a fin plate for form wings. Secondary airplane main to frontal wings make lift, but in our case, beside wing drag force in x-axis direction, we have frontal nose drag force Fd. Airplane nose drag coefficient value is CD equals 0.63. We see how to calculate nonlinear shape drag coefficient, which has cross-section area 0.196 square meters. K equals 4, which is a number of wings. They all are identical, and with the possibility of the angle of attack variable pitch shown here. Single wing length is 1.5 meters, width 0.4 meters. Single wing surface area is equal to 0.6 square meters. Wind stream air density is aerodynamic in wind tunnel is equals rho equals 1.2 kilograms per cubic meter. The aircraft model mass is 70 kilograms. Therefore, the gravity force of aircraft is 686.7 newtons. Maximum wind pressure is equal to 1215 pascals. This value also sustains energy conservation condition. For a turbine, you cannot convert all wind velocity kinetic energy into torque rotation velocity. The same condition applies to wing lift force. Numerical source of wing variable pitch attack angle theta value under the condition that airplane 4 has wings lifting force is in equilibrium with gravity force. Lifting force equilibrium is in straight and level flight position. Force is in the y-axis direction. The result is equal to 14 degrees. and was obtained by using double-angle sine trigonometric identity. Total airplane drag force in x-axis direction is equal. The actual airplane's purpose is not to produce lift force but to make flight from airport A to airport B shortest motion and shortest time duration in x-axis direction. Lift force is a negative factor in aviation that reduces total velocity and fuel consumption efficiency of airplanes. Vehicles have drag coefficient of soft tires with surface and bearings friction forces, but compared to aviation driving drag coefficient on the ground is significantly less resistant than keeping the airplane in the air. The resultant force and required engine thrust for our thought experiment are: the result was obtained by applying Pythagoras theorem for right triangle. Typically, engine thrust is measured in tenths of hundreds of kilonewtons, but in our case we have a small aircraft model in the wind tunnel weighing only 70 kilograms. Vector addition of forces is in straight and level flight position. Only x-axis forces is matter. This fact be important later. Dividing the equation fx term accordingly by area A and A0, the result is the total pressure loss delta P due to airplane motion in a straightforward direction in the x-axis direction. Velocity to overcome drag pressure loss in the x-axis direction is equal to energy quantity to keep the airplane in a straight and level position at steady velocity W0 equals 45 meters per second is equal to present internal combustion engine have gasoline energy efficiency factor equal to 0.3. Caveat regarding efficiency: 0.3 is an average value for gasoline-driven vehicles where a fuel combustion energy is transferred to wheels. For aeroplane propellers, efficiency value can have a different value. Gasoline heat energy capacity per kilogram is equal to 43 kilojoules per kilogram under the condition of steady wind or actual aeroplane velocity W0 equals constant. The energy measurement unit and power measurement unit energy change rate per 1 unit second have equal quantity magnitude 26.6 kilowatts. Thus, gasoline consumption per 1 hour is equal to 7 kilograms per hour. Equation is essential for energy efficiency, airplane and vehicle design because our velocity in a wind tunnel is 45 meters per second, but an actual airplane of such proportion with an engine must produce thrust equal to 72.6 meters per second. We reverse engineer our mathematical model and solve velocity loss 27.6 meters per second due to drag force in flight. That is a useful mathematical method for people who are interested in physics. The calculation of airplanes and regular vehicles of various masses and with various types of force-producing engines It also explains the inertia of aircraft in flight. If the engine is turned off, airplanes will not fall from the sky immediately. It will move in the sky with inertia, and only drag will make the plane slowly descend. That is how gliders fly without an engine. Only initial towing speed is required. All present forces in the y-axis and x-axis can be written as an equation system from the wing angle of the attack variable. In the equation system, we see that airplane Fy lifting for drag force and straightforward Fx drag force is multivariable solution problem from the wing's attack angle variable theta. That is a property of multivariable functions, where each coordinate system are linked through one variable. It solves pressure loss in x-axis direction and at the same time indirectly equation estimates lift drag pressure loss in y-axis direction from one variable wing angle of attack theta. I recommend to watch my video titled Multivariable Based Physics Problems. The video essay explains the difference between single variable and multivariable physics problems. Here is another of my recommended video. Rocket Science Part 1. Rocket velocity in y-axis direction is single variable formula from time variable t. Here from time t variable rocket velocity in y-axis direction changes in 3 places. That is real rocket science, a hard physics problem to solve, but in general multivariable physics problems are harder to solve than single variable physics problems. Also, I am not trying to downgrade one variable physics problem, which have exceptions from the rule. That is not just philosophical question, but also practical and at the same time confirmation of my theory. First, we apply boundary condition in the y-axis direction for high-velocity ballistic rocket. We see that at a high-velocity angle of attack approaching zero value because pressure P0 in the denominator of inverse sine function approaching infinite value. Cross-section area A0 of a cylindrical shaped ballistic rocket is enough and wings are not needed. Contra-argument is without engine and with long-span wing gliders. Here we have another huge term, which is the total surface area of 2 main wings. It has tail wings called stabilizers. They regulate yaw angle regarding x-axis direction. Compared to lift wings surface area, they are negligible. It can create a notion that rockets and gliders have no comparison vice versa, and they operate at the same principle, increasing denominator value and decreasing numerator by reducing aircraft's mass. And yes, glider fuselage is made from light materials, for example fiberglass, which has lower density than wood. But this is not true. Gliders carry extra weight, ballast inside the fuselage as a water tank storage, very similar to how hot air balloons or hydrogen and helium air balloons uses to control ascending and descending with sandbag ballast mass. We investigated a wing with zero thickness, but the real wing has thickness delta. Gliders has very long wingspan length L. For this reason, wing geometry induces high drag forces made by wing thickness alone. Gliders have lift-to-drag ratio criteria. In our case, for glider is towed when it reaches maximum altitude with a maximum velocity of a W0 they let go to glide freely. In that case, the glider will start to descend, and in that case, the mass of the glider can be beneficiary because higher mass under the wings creates a bigger counter wind, which will, according to third Newton law of motion, will create a higher lift. That is counterintuitive. Extra mass as ballast for a glider creates extra negative velocity air cushion, which allows gliding further than lighter glider. It's a recursive mathematical relation based on the third Newton law of motion. Forces create equal counterforce. For a glider, only initial pressure P0 is known. Later pressure can be changed due to lack of thrust and with wing flaps. In y-axis direction, force is negative because the glider at the vertical wing flap slowly descending. Twice velocity in y-axis direction has negative sign. For race cars and Formula 1, very light cars use wedge-shaped spoilers to create downforce to keep the car glued to the racetrack and not thrown away on sharp corners under high velocity. Here we see that the shape of the wing is not important. In very straight segments of a racetrack, spoiler is a negative factor that reduces velocity in straight racetrack segments. Stall phenomena induced by wings will be investigated in the upcoming chapters. The answer, do airplanes need wings, is yes. The most important wing application is aircraft liftoff and landing regime. In the liftoff position, every aircraft with the engine is heavy and full of petrol in tanks. In the landing position, velocity is at minimum, and all lifting in both situations done by wings at a high value of angle of attack. The previous chapter solved airplane motion for steady cruising speed condition, in which case the airplane stayed in a straight and level flight position. This chapter solves a case of an airplane ascending in altitude at a velocity of wind 45 meters per second, but the wing angle of attack increases from 14 to 16 degrees. Thus, equation system will obtain such expression. The juxtaposition between straight and level flight position and ascending at a steady and equal velocity engine thrust is drag force values. The resultant force of ascending aircraft mode is higher even if velocity is the same in both situations. Ascending angle phi solved according to the rule of tangent to right triangle. Velocity of ascending in the y-axis direction is equal to, let's say after 1 minute, which is 60 seconds, aircraft will climb 243 meters in altitude. The steady velocity of 45 meters per second in the x-axis directions. First, extra angle of attack and extra climb altitude gain will be expressed through extra fuel consumption compared to the straight and level flight position. It is a physics problem, but it can be a very well applicable tool for engineers to convert various flight options into numerical values for petrol consumption for a particular aircraft. Aircraft descending have a bit different condition than ascending mode. Here, instead of a wing angle of attack pitch change, we keep the same angle of attack as a straight and level flight position, but this time change maximum velocity from 45 meters per second as was in the straight and level flight position to 43 meters per second on right side of a comparison board. Aircraft descending resultant force Fr, angle phi, velocity, and y-axis direction are equal to. For engineering purposes, a minus sign for force in the y-axis direction is not necessary. It can be an absolute value. Negative sign as a physics solution has meaning. It shows three possibilities for aircraft to be in a straight and level flight position in y-axis direction. We have zero value. Aircraft ascending, we have greater than zero positive force value. Additionally, we need to estimate the force of a wing in the y-axis as the aircraft ascends and descends. In our case, velocities are not very high, so it is an ideal estimation. Even for propeller-driven aircraft losing engine thrust, aircraft can successfully glide to safety on the ground if it has a landing surface and enough free space to do so. The last step is to compare engine petrol consumption. Descending losing engine thrust under the equal angle of attack of the wing mode is more economical than climbing in an altitude situation. Stall mode of aircraft is a situation when under a very steep angle of attack aircraft engine thrust is not enough to stay aircraft in the air or to climb altitude, and the aircraft starts to lose altitude by falling. Falling is not a bad thing if your aircraft is at high altitude at that time. If a stall happens at the liftoff moment, when the aircraft just started to climb altitude and suddenly stall happens, that is dangerous situation. Aircraft can crash. Our solution will be different. We try calculating the maximum velocity at which an aircraft must fly when the wing angle of attack is at maximum angle of 45 degrees. This angle is the maximum value for a stationary turbine blade. For moving aircraft, steep angle of attack means a lot of drag in the x-axis direction, but our philosophy of physics is to show aerodynamics from the perspective of engine thrust or maximum wind velocity in the wind tunnel or maximum wind velocity for turbine blades for windmill. This steep angle at which aircraft stay is in a straight and level flight position consumes a lot of energy compared to a velocity of 45 meters per second and under the 14-degree angle of attack. It is a paradoxal, but a steep angle of attack is a negative factor. In the case of a glider, where angle of attack is a small, wide span of wing creates additional drag because wings have thickness. For aircraft, if you want an engine with a higher thrust, it will be heavier engine requirement, which means extra thrust to compensate for extra weight. From the perspective of math, function to solve physics problem of lift when we have 6 parameters. Every time we change some parameter, for example, high surface area of the wing also increase the mass of total airplane of the total airplane. In civil aviation, for wide-body fuselage airplanes, wing plays a role as the extra fuel tanks. For people who are interested in multi-complex physics problem, it's an interesting mathematical problem with many parameters and 2D variables involved. For example, Formula 1 has a race rule that all racing cars must use 1.6-liter engine, and with all spoilers to create downforce. In the end, it has very low frontal cross-section area A compared to everyday 1.6-liter sedan vehicles on our streets. You can call the F1 racing car a not very spacious car. The task is to create a low-profile cross-section area that induces very low drag force. Another example is Boeing 787 Dreamliner, where 50% of its weight is made from composite materials, mainly carbon fiber, which is less dense than aluminum, which is very light and very durable material. It means it can carry less fuel, and with new efficient engine is more efficient. Additionally, carbon fiber allowed create a very thin wings frontal profile, thinner than fiberglass glider, which additionally reduce frontal drag and weight. I know aerodynamics engineers tried to bite more than they could chew, tackle 3 independent parameters at once. For wide-body fuselage planes, weight is the biggest enemy, which increases petrol consumption, which means cost of tickets and a lot of CO2 and heat released into the atmosphere per passenger. Aviation-grade aluminium is well-established material, yet it is heavy compared to carbon fiber or fiberglass. On the other hand, it is well-tested material in aviation. New material usage in aviation requires a lot of research and development and a lot of time on site testing. In ascending mode, we show an example where velocity W0 is constant and we change only the geometry of a wing angle of attack. For stall mode, we show we can reduce velocity in x-axis direction by overcoming drag forces by a very powerful engine. First, drag force is a function of geometry shape from wing geometry is the angle of attack parameter. For all types of aircraft, including gliders, resultant force is responsible for various modes of airplane flight position. For gliders, it is slow descending on an air cushion created by gush of wind under the wings. Our physics was solved using reverse engineering method. Thus, velocity in x and y axis direction is a function of 6 independent parameters. That is all, folks. Thanks for watching.